Hi, let's look and see if we can write a report on analysing how we might reclaim silver or produce silver from two different processes. One using an electrochemical cell and the other using an electrolytic cell. So as you can see on the slide here, we have electrochemical cell on the left, or galvanic cell, has two half cells connected by a salt bridge, and on the right we have an electrolytic cell where we will carry out electrolysis. Now, let's go and see what we need to do to produce a comparative report that will meet the standards of Achievement Standard 91393. So on the left, you can see that we have a picture of the setup of the galvanic or the electrochemical cell. The left half cell contains iron nitrate, iron 2 nitrate, and an iron electrode, and the right hand side contains a silver electrode and silver nitrate. So what we have to identify for a start is what is the oxidation or reduction reaction happening in the left hand cell and what's happening in the right hand side. Usually by convention we're going to draw the reduction on the right, but depending on how a specific experiment was viewed, whether it was reviewed from the front or the back, we might have it flipped around. In this case, we do have the reduction happening on the right, but how we know that is if we look at the redox couples, we can see that we have three potential redox couples that are happening here, and the most positive one is going to go forwards, but what we can see is that the redox couple for O2 to H2O involves O2 being in the solution. Now, we would expect that there's not a high concentration of O2 in the solution because it doesn't say that, so we're going to exclude that one. So we only have the silver iron to silver metal, and the iron 2 plus iron to iron metal electropotentials to look at, and the silver one is the more positive one. So that's going to be the forwards reduction reaction that happens. It's going to go in the direction it's written. So let's just state that. So the reduction potential of the silver plus to silver iron is more positive than Fe2 plus to Fe couple, so it's written as reduction. So let's write it as reduction. So that means we're going to put Ag plus on the left and Ag on the right. We're going to add the states to them. Now, because this is a silver nitrate solution, the Ag plus is going to be soluble in water. It's going to be dissolved in water, so it's going to be aqueous. And we can see here that the silver is in the form of a solid electrode. So when we write it down, we're going to write silver iron aqueous goes to silver solid. And then we're going to balance it. The silver is balanced on both sides. There's one silver element on both sides, or atom. There's no hydrogens or oxygens to balance, so now we're just going to balance the charge, so we'll add an electron to the left. So the next thing that we're going to do, so we've drawn the reduction equation. Well, we need to state that it's the reduction equation and give an explanation as to why. Not the explanation based on the reduction potentials, but by looking at this equation, how can we state that it is reduction? So the first thing we can say is each of these silver ions gains, because the electrons on the left hand side, it's gaining electrons. Each silver ion gains one electron to form one solid atom. Okay, now when I explain this using electron gain or loss, here we need to be specific in the number of the electrons that need to be gained by the reactant. In this case, it's a silver ion, silver plus ion, and it needs each silver plus ion needs one electron to become one silver solid atom. Okay, but we can also explain this as reduction by using oxidation numbers. And when I'm writing a report, I'm going to write both down. So if I do make a mistake with the proportion of reactants to electrons, then that can be corrected by my oxidation number one. So let's have a look at what we would do here. So we're going to say that the silver iron, because it's an iron and it has a +1 charge, it's going to have an oxidation number of +1. And the silver solid here on the right hand side is an element. It's an atom by itself that's neutral, so it has an oxidation number of 0. You can see as we go across the arrow, across the equation, the oxidation number of the silver atom in both of these species has reduced from +1 in silver plus to 0 in silver. So we write that down. This is my first sentence here. Now, I have to be specific here. It is the reactant that is being reduced. Okay, so we always choose the species that's the reactant that has the atom in that's changing its oxidation number. We state that it's the silver atom that's changing its oxidation number. It's decreasing because it's a reduction. And we state what the oxidation number is in the given species. So it's +1 in silver plus and 0 in silver. Now I've taken the opportunity here, because I need to for this report in the standard, is link what we observed to what's happening in the reduction equation. Now, because this is reduction always happens at the cathode. Now we remember that because both reduction and cathode start with consonants, and we know that oxidation happens at the anode. They both start with vowels. That's how I remember that in my head. Okay, so here we know that this is happening at the cathode. So the cathode is increasing in mass. Does that make sense? Yes, it does. Because look, we're making silver solid. Now, if silver solid is being made, it's going to deposit onto the silver electrode that's already there. It's going to add to the surface of it, coat the surface of the silver electrode, and that means it's going to get heavier if we weigh it, because it has an increased in mass. So we say the silver solid produced deposits on the cathode, increasing its mass. Linked to the observation. Okay, that's our reduction half equation. What is our oxidation half equation? Well, if the two redox couples are the silver and the iron redox couple, if one goes forwards, the other one must be oxidized and go backwards. So that means we're going to have to put the Fe here from the electrode, that's the Fe solid first, and the Fe2 plus, that is aqueous, it's part of the iron 2 nitrate here. We're going to write that in our equation, but we're going to write Fe first, Fe2 plus second. Remember, we put the states in. We know that the Fe is in a solid state because we're told here, or we can see that the electrode is a solid piece of metal. Now, because here the Fe's are balanced, I have one iron atom in the solid here and one in the iron here. Okay, but we can see that the charge isn't balanced. So we're going to add 2 electrons to balance the 2 plus charge and make it neutral charge on both sides. Now, next thing, we're going to explain whether this is oxidation using loss of electrons. Now remember, Leo, the lion, goes Gur. Loss of electrons is oxidation. That's Leo. Gur, gain of electrons, reduction. This is losing electrons because they're on the right-hand side, so it's oxidation. This half equation is oxidized because each of the iron solid loses 2 electrons to become 1 iron 2 plus. Okay, so I'm putting the specific ratio of how many electrons are lost from each of the reactants and saying how many products I make in a mole ratio. I can also explain this, remember, using oxidation numbers. So let's go ahead and give the oxidation numbers above this equation. So the iron solid, this is an element, so oxidation number of 0. The iron 2 plus, it has an oxidation number of +2 because it is an iron. Now, if we look at the oxidation number of the iron atom in both iron solid and iron 2 plus, we can see it is decreasing. Therefore, increasing. What did I say? Decrease. It's increasing, therefore it's oxidation. So we can say the Fe solid, the reactant here, is oxidized because the oxidation number of the iron atom is changing from 0 in Fe solid to +2 in Fe2 plus. Now, if your teacher is likes to use the phrase oxidation state instead of oxidation number, anytime in this video I use oxidation number, just replace it in your head with the term oxidation state. Okay, so what happens here? Well, this iron solid can only come from one place. It comes from the iron electrode, and it turns into this iron 2 plus that is soluble in this solution. So what we have to say here is link what's happening in the equation to what is observed. The anode decreases in mass, and remember, the anode is the oxidation that's happening because they both start with the vowel here. So the mass of the iron anode will decrease because the iron solid is reduced to Fe2 plus ions. If you want to make a more robust explanation, you can say because the Fe2 plus ions are soluble. Now you might also have here, someone might give you the observation that around the anode the green color gets slightly more intense, and you would explain that because as the iron solid turns to Fe2 plus ions, the concentration of Fe2 plus ions increases, increasing the intensity of the green color. Okay, so we've put both the half equations here. What we can do now is we can add the two half equations together. Now notice that in the first half equation we have gained 1 electron, and in the second one we have lost 2. There has to be an equal exchange between the oxidation and the reduction process. So in order for that to happen, I need the top equation to happen 2 times, which means multiplying everything in the equation by 2. And then once I've done that, I can cancel the electrons out and add all of these together in one final equation. So that would be 2Ag plus 2 electrons goes to 2 solids. I would then cancel the 2 electrons at the top with the 2 electrons here, and I would get 2Ag plus aqueous plus iron solid will make 2 silver solid atoms plus an Fe2 plus iron. Okay, that's our fully balanced equation. The next thing we need to do is work out the E cell. Now for a galvanic or electrochemical cell, the E cell is going to equal the right hand electrode minus the left hand electrode. So what I mean by that is we look at the picture that we have, and the right hand electrode is the one that's on the right hand side in the picture. So that's the silver electrode. So we're going to take the reduction potential value for this silver couple here, which is positive 0.80 volts, and we're going to subtract away from it the redox couple for the iron cell, half cell here. So we plug those in, and notice because the left-hand electrode reduction potential here was negative, and we're subtracting it, that is going to resolve itself into a positive. So it's going to be plus 0.8 plus 0.41, and the answer we get is 1.21 volts. Awesome. So the final thing we would have to do if we're writing a report comparing electrochemical and electrolytic cell for the electrochemical part of it is just to summarize what that means. Okay, so what this means is because this is a positive voltage, this reaction is spontaneous. Also, because this is a positive voltage, we are producing electrical energy. We could also say that because this is a positive voltage, the equation as we've written it will go in the direction we've written it. So it means that it flows as we said. Now, if by chance, remember I said the diagram could have been flipped around the other way. If it was negative, electrochemical cells are always spontaneous. Okay, so they're always spontaneous, but it means the reaction would actually happen in the opposite direction than we wrote it. Most of the time they're going to give us one that gives a positive voltage. Okay, let's go to look at electrolytic cell now. Oh wait, before we do that, let's just look how this would be marked for achievement standard 91393. Okay, so you actually have to compare the reduction potentials to identify which one will be reduced from the couples. That's an achieved mark here. And we can get the voltage, but this is an easy way to gain that. And then the next thing we need to do for achieved is we need to explain why it is oxidized, why the first one's reduction and the second one's oxidation equation. We could use either the loss or gain of electrons or the change in oxidation numbers, but they have to be a correct statement. You can use either of those. That's why I've suggested that you write both of them down in case you make a mistake in one. Now, to get a merit grade, you need to do those three things, but also you need to balance your half equations, and you need to explain the observations. Okay, balance the half equations correctly like they are. Explain the half equations. Okay, so you're linking what you have, what's happened in the half equation to the observations that you're given. And then finally, to get the merit, you need to get the correct voltage. Excellence, two major points here that we need to do: balance the full equation and write the statement at the end telling us that because it's positive, it's a spontaneous reaction, and because it's a positive voltage, where the reaction happens in the direction it's written, and there is electrical energy produced. Make sure you say electrical energy and just not energy, because it's producing electricity. Right, let's go on and have a look at electrolytic cell. Okay, so this electrolytic cell, in this case, we can see that actually it's in an aqueous solution. So there's two types of electrolytic cell we normally meet. One is that we have an ionic solid that's been heated quite hot to a high temperature, and it's turned to a liquid or a molten mixture. Okay, or we can dissolve the ionic solid in water and we have an aqueous mixture. Now usually you would, in this case, we can see that it's an aqueous mixture because it has AQ after the silver nitrate. Now I've written down also that there's water in this, and you can see that there's a couple observations here. On the cathode, we have a silver deposit is formed, right? And we have a gas, a colorless gas, coming off the anode. So remember, we're going to have to link that to our half equations. So what are the two redox couple that's going to happen here? Well, I've given 3 here, but we can see it's not going to be the iron 2 plus the iron. There are no iron species in this cell. But we do have silver ions, Ag plus, in the form of silver nitrate. So when silver nitrate is aqueous, it's really just silver plus ions and nitrate minus ions, right? We also have water in here, which is part of this redox couple here. Now, because this is an electrolytic cell, which is not spontaneous, there's a power source at the top providing the electrical energy, the actual couple that is going to be reduced is the one that is most negative. So it's opposite to the electrochemical cell. So here, my reduction one is going to be the silver again, because if we look at the silver reduction potential of positive 0.8 and the oxygen one of plus 1.23, we can see the silver is more positive. It's going to be written as reduction. So we write this as reduction, and it will look similar to what we did with the electrochemical cell, exactly the same. And in this case, because it's the solid being produced on the electrode, actually our explanation is going to be very similar. The half equation is reduced as each Ag plus ion gains 1 electron to produce 1 Ag plus solid. Now, if by chance this was taken in a molten mixture, remember that in a molten mixture, often the metal, when it's formed, is in a liquid form because it's a really high temperature and it's melted. And also the ions are liquid because it's in a molten mixture. It's not in this case, so we don't need to worry about that. So the same explanation oxidation number is the one that we did in the electrochemical cell. It's a +1 going to a 0. So we have the silver ion is reduced because oxidation number of the silver atom decreases from +1 in silver ion to 0 in silver solid. Now notice everywhere I've written things down, I've tried to include the correct chemical terms and I've tried to include the states. If we're doing actually this report for Standard Achievement Standard 91393, one of the particular points you need for excellence is that you're consistently using correct chemical language and symbols. So that's why I'm making sure I'm being precise with what I write. So the silver solid is produced, or the silver solid produced, should be a comma here really, deposits on the cathode. Yep. Remember, I'm using the word cathode because I'm using the correct terminology. And I'm not using the word cathode here. I'm using the word anode. No, cathode is right. I'm using the word cathode because this is getting reduced. I'm using, instead of saying electrode, which is more generic, I'm saying cathode, correct terminology to make sure I do get my excellence grade for this. Now this is observed as a silver deposit, see? So they didn't say that they measured the mass here, they just said that they noticed a deposit on the outside of the inert carbon electrode. Okay, so that's cool. That's got us to that point. So now we're going to do the oxidation equation. Now in this case, we've got 8, it's going backwards, this one, because it's oxidized, right? So start with H2O, we're going to O2. Now, because we have in the O2 molecule 2 oxygen atoms, we're going to need 2 waters to provide 2 oxygen atoms. So once we put the coefficient in front of the 2 waters that are liquid, of course, it's in the liquid phase, yeah, we now have 4 hydrogens. So we have to go over to the right hand side and balance the hydrogens by adding H pluses, if you remember your balancing rules. Once we've added 4 H pluses, we need to add 4 electrons to make the charge the same on both sides. And on both sides, the charge is 0 now. Now, this half equation, let's be careful here. So we can write it this way. We can say for every 2 H2Os, right, we are losing 4 electrons to produce 1 O2. So I'm really just describing in the correct ratios what's happening in the equation. But of course, I don't have to talk about the H plus because it's not involved in the oxidation reduction. And in fact, the oxidation number of the hydrogen is +1 on the left and +1 on the right. It doesn't change. So that's why we're talking about the oxygen when we talk about oxidation numbers. So let's put the oxidation numbers here of oxygen. It's -2 in water because it's a compound, and oxygen is -2 in a compound, except if it's in a hydrogen peroxide, okay, or a peroxide. There are other types of peroxides as well. Here in O2, the oxygen, you have to remember here that if you have an O2, it's an element, so the oxygen is now a 0, even though usually it's a -1 in everything. So what we can say here is that the H2O is being oxidized because the oxidation number of the oxygen atom in it has reduced from -2 in the water to 0 in the gas. And then linking this to the observation is quite straightforward. The colorless gas observed at the anode is the O2 that's produced. Awesome. Okay, so we want to balance these. It's similar, but a wee bit trickier than the other one. So we've got 4 electrons here, so of course we're going to have to multiply this first equation by 4 to cancel out the electrons. Now take care when you write this down that you remember all the terms. So you have to put in 4 Ag plus 2 waters goes to O2 plus 4 Ag plus 4 H plus. So remember, you've got all of the terms, and check that you put all of the states and you've got the correct charges. Once you've written it, check that your charges are balanced too, because that'll often, if they're not, you'll pick up what mistake you might have made in your equation. Okay, so this is that part of the report written. So the final bit we need to do is calculate the E cell. Now to calculate the E cell for an electrolytic cell, it's slightly different. We don't have we don't talk about the left-hand electrode and right-hand electrode here. We just go the E cell equals the reduction minus the oxidation. So you have to remember the slight difference in the equation here. So what's been reduced? Well, that's the silver. So we're going to chuck the silver couple in here plus 0.80, and what's oxidized is the water here, so that's plus 1.23. Now take care here, if you've got it around the wrong way, you're going to get a positive number. If you've got it around the correct way, you're going to get a negative number. So here, negative number, awesome, this is an electrolytic cell. Now we have to remember, because it's an electrolytic cell, it is non-spontaneous. The things that we are saying are reacting together here do not react together naturally. They only react together because the power source is removing the electrons from the water and giving them to the silver. Okay, so it's providing the electrical energy for the process to happen. So that means that this must be a negative value, and we have to explain that because this is a negative value, this is not spontaneous, and the reaction requires electrical energy. Okay, so it's important that you again say that it's electrical energy. You can also say that it has to be at least 0.43 volts. Right, it's got to be larger than that in magnitude. and just chuck the value in here just to be, I guess, make sure that you've got all the detail in there. Okay, so finally we've looked at an electrochemical cell, we've looked at an electrolytic cell. Let's just summarize them. Before we summarize them, let's just check what we need for achieved. To achieve here, we need to talk about, explain why it's oxidation reduction. Remember, we can either do that through loss or gain of electrons, or we can do that with change in oxidation numbers. The other thing that we need to do is say something about this being not spontaneous because it's negative. That's needed for the achieve point. Okay, we have to have some understanding that the power is the energy, the electrical energy is being supplied because it's not spontaneous. For merit, balance the equations, the half equations, not the full one, balance for merit. And then you need to link your equations to the observations, right? The other thing you need to do for merit is the same for the other one, is you need to give the voltage correctly. Excellence, balance for equation, and then the summary at the end. Now, as well as that, also, it's a good point that you now go and summarize both of these reactions. You put a summary at the end. So let's just go over that very quickly. So here's our two cells. So we're going to talk about what's the same and what's different. So the actual thing here is they wanted us to compare and contrast the collection of silver from a waste solution using electrochemical and electrolytic cells. Okay, so we're going to say, we're going to talk about, do they both produce silver? And the first thing we can say is both of them can produce the silver metal. Both the electrochemical and the electrolytic cell can produce silver metal. Okay, so that's the thing that's similar about both of them. It might not always be true, and if it's not, you say one does and one doesn't, but that's okay. In this case, they do. So what's different about them then? Well, remember, if we go back to the electrochemical cell, it produces electrical energy and it's spontaneous, where the electrolytic cell uses electrical energy and it's not spontaneous. And that's most probably the most important thing to state. Okay, silver produced spontaneously, electrochemical cell produces electrical energy, where electrical energy needs to be supplied to produce silver, an electrolytic cell, because it's not spontaneous. Last thing you could talk about is if we look at the setup of the electrochemical cell, it needs two containers, two vessels to carry it out. You need a salt bridge, need two separate solutions. Okay, can you see that? So I could compare that. Well, on the right hand side, the actual electrolytic setup is a lot more straightforward. I just need one container, two electrodes, and one solution. And that would be the end of our report. We'd hand it in, and if we put everything that I said here, you'd be getting an excellence grade. Good luck with your work from here on in. If you need any other help, look at the other videos I've done on electrolysis.